So in part 3, we're going to talk about decomposing variation in the outcome and calculating measures of fit. Because when you fit a least squares line to a set of data, sometimes it will fit better than in other cases. And it's useful to know how well this line is fitting the data. Let's look at Galton's example of inherited stature. So this is from his 1885 paper on regression towards mediocrity in hereditary stature. And if you recall in this paper, he developed the technique of simple linear regression. As a result of minimizing the sum of squared errors, we obtain this simple linear regression model, in which the intercept is 22.38 and the slope is 0.64. So we get this line going through this scatter plot of data. As we mentioned previously, and we talked about, one consequence of minimizing the sum of squared errors is that the intercept and slope have particular properties, right? The errors or residuals, as well as the predicted values of the outcome, or the fitted values, the y-hats, they also have several unique properties. So let's look at some of these properties. The least squares properties of the errors, or the residuals, one of them is that as a result, as a consequence of minimizing the sum of squared errors, if you take the average or mean of the errors, that is 0. So the average of the errors, that's 0. Right? They're equally likely to be above and below this value of 0. As well, by minimizing the sum of the squared errors, if you add up all the errors, that is also going to be 0. Intuitively, what these two properties are telling us is that the regression line, it's just as good as or bad as it is over predicting. Right? You're going to have residuals above and below that regression line. Right? It's not constantly over predicting, it's not constantly under predicting. Right? It's going to be above and below that line. Right? There are also several least squares properties of the fitted values, or the y-hats. Another consequence of minimizing sum squared errors is that the mean or average of the predicted values of the outcome and that for the actual outcome are in fact the same. So if we look at the summary statistics for the raw values of our outcome, the raw value has an average or mean of 66.76 inches. If we look at the predicted values of our outcome, that average is identical within rounding error. This is interesting because it tells us that overall, in terms of like the average calculation for our outcome, the y and the y-hat have this similarity, right? They're not all that different, at least in some of the summary statistics. Also, we can look at various correlations and predicted values and errors. When we look at all these different correlations, they also have some interesting properties. So we're going to look at the correlation between the fitted values of our outcome and our input variable, or x variable. We're going to look at the correlation between our errors or residuals and our input, or x variable. And we're going to look at the correlation of our y-hats with our errors. This will help us understand the properties of these errors or residuals that we obtain from simple linear regression, and it'll also help us decompose the variation in our outcome. So what is the correlation between our y-hats and our x variable? You can think of this as, in the context of the Galton example, these are the predicted or expected values of the height of children based on the actual or raw value of the height of the parents. Well, what's the correlation between these two? Well, the correlation is in fact 1. That's because all the y-hats, they fit on the simple linear regression line. And so in the limit, a correlation, if it's a correlation of 1, it's going to look like a line. All those points are going to lie on a line. And so in this case, you can see for every x value in our data set, those y-hats, they all fit on the line, and that correlation is perfect. It's a 1. Right? This is a consequence of minimizing the sum of the squared errors. Those y-hats are going to fit on that line. We want to ask, what is the correlation between our errors or residuals and our input variable, our x variable? Well, in fact, that correlation is 0. Right? This is an interesting point, because what this is telling us is that we can think of our outcome, right, as having these two components, the y-hats and the errors. Right? In order to back calculate or recapture, recover the raw outcome for each individual in our data set, all you need is the y-hat and the error, or the residual. And you can think of each outcome value in terms of the fitted part and the residual part. But the other interesting point is that that fitted part is perfectly related. to our x variable, and the residual part is completely unrelated to our x variable. So you can see that we can think of our outcome as being due to that variation which is related, perfectly related to our input variable, mid-parent height, and that part of the outcome which is completely unrelated to our input variable, mid-parent height. Another correlation that we might want to look at is this correlation between our fitted values and our residuals, or errors. And as a consequence of minimizing the sum of squared errors, we find that the correlation between the y-hat and the errors, or residuals, that's 0. So the fitted values on that line and those residuals, those errors, they have no relationship whatsoever. So let's look at a summary of these correlations. We look at the correlation of our fitted values and our input variable. They're completely correlated, correlation of 1. Intuitively, you can think of that because all those y-hats, they fit on a line. So for every x value in our data set, that y-hat's going to be on a line. And in the limit, a perfect positive correlation in this case, it looks like a line. The correlation between our errors, our residuals, and our input variable, that's 0. Right? So the errors or residuals, they're unrelated to mid-parent height. Then the correlation between our fitted values and our residuals, that is 0. So all those points on the line and all the residuals, they have no relationship with each other. This is useful for thinking about decomposing the variation of our outcome, because you can say, well, we have that part of our outcome which is predicted or related to x, and we have that part of our outcome, the errors or residuals, which is not predicted or related to our input variable. So we will use these correlations to help us understand how to decompose the variation in our outcome. And it's that topic, that decomposing the variation in our outcome and measures of fit that we can derive from that decomposition, that we'll explore in just a moment.